This is lecture 21. We're going to be talking about recurrent versus transient classes. So just to remind you of what it means to be accessible. So basically, if there is some positive probability that in a certain number of time steps in that you can go from state I to state J, then it means that you're accessible from state I. So here, J is accessible from I. Here J is accessible from K as well. K is accessible from J. So we're going to let A of I denote all the accessible states from state I. So in other words, if there's a J in A of I, then it means that there's some probability that there's some number n, so that there's a positive probability that within those n time steps that you can get from I to J. So an example here, if I have this example here, I have 5 different states. If I look at this, again, I can identify my communication classes. My communication classes are 1, 2, and 3. And then 0 is by itself, and 4 is by itself. So 0 and 4 also has the additional property that they're closed, because once I'm in there, I can't get to anything outside of there. So if I look at what these A of a state is, so like for instance A of 3, what states are accessible from 3? Well, I can get to 4 from 3, I can get to 2, I can eventually get to 1, and I can get to 0. So all my states are in 3. So here, if I'm in state 0, what's accessible from 0? Well, I can get to myself, I can get to anything else. So A of 0 is 0. Similarly, A of 4 is 4. Okay, so now what does it mean to be recurrent? So a state I in S is recurrent if I is accessible from every state that is accessible from I. So in the above example, state 4 and state 0 are called recurrent because I can get to everything in its accessible. So I can get to everything in its A of 0, A of 4. I can get to all of everything's accessible from each other because there's only one number, right? 0 or 4. However, I can get to 4 from 3, but I can't get to 3 from 4. So this is not recurrent, so it's transient. So if a state is not recurrent, we say it's transient. If I is recurrent and J is in A of I, then J is also recurrent. So if they're in the same communication classes, if one state is recurrent, then the other state is also recurrent, and vice versa with transient. So this naturally means that if a Markov chain is irreducible, so all of the states are in the same communication classes with a finite space, then we say the states are always recurrent. It's a little hard to think about it if it's infinite, that the states can either be recurrent or infinite. We're not going to really talk about that. We're going to stick with finite Markov chains. Okay, so when we have these finite Markov chains, we can talk about the first return to a state I. So this is the first return is denoted by Fii of n. So basically this is just the probability that if I start in state I, what's the probability I'm going to be back in state I in n time steps. So the way this is written is Fii of n is the probability that at the n time I'm back at I, but I was not there at any previous time step. So it's the first time I return. So what's the probability that in the n time step I'm at state I, even though I wasn't there at all before? And just for notation purposes, we call Fii of 0 is 0. In general, what's the probability that I'm going to get from state I to state I in one time steps? Well, that's just denoted from our probability transition matrix. But in general, this isn't true. In general, my first return is not my probability of going in n time steps. What we do have is that Fii of n is probability, so it's between 0 and 1. If it's transient, what that means is I can get from, if it's transient, then I can get to other states from that state. So there's a possibility that I actually don't come back to my state I. So the sum is strictly less than 1 in that case. If it's recurrent, then it means I'm always going to be coming back, that there is always a possibility of getting back to my state. So that means if I take the sum over all time steps n, then my FII of n has to equal 1. So again, this is just kind of giving you the terminology again. So looking back at this example, so if I look at state 3, here, remember this was transient, right? So if I look at state 3, I could go this way, back, and back, right? So there's a possibility of a return, but I can also leave the state and never return. Now here, remember 0 was recurrent. 0 is recurrent, I'm always going to come back to it, right? There's always the possibility of me coming back to it. So once a state enters a recurrent class, then it basically means that it's going to be in that class forever. Transient classes always, the transient states always end up going to a recurrent state. And then once it's in the recurrent state, it stays there forever. Okay, example, this one has 3 different communication classes. 1 by itself, 2 and 3 communicate, 4 and 5 communicate. So states 1, 4, and 5 are recurrent or persistent states. So remember, recurrent means I come back to myself. Transient means there's this possibility that I'm going to leave and never come back. Here, in this example, both 1 and 4 and 5 are closed because once I'm in this state, then I can never get out of the state over here. And 2 and 3 are transient. So possible paths from state 2, I could go to 2, 1, 1, 1. Or I could go from 2 to 3 to 2 to 1, 1. Or I could go 2, 3, 4, 5. 4, 5, 4, 5, 4, 5. So I get stuck in there, right? So a recurrent class can be either considered to be periodic or aperiodic, depending upon the period of the states within the class. And so next time we're actually going to give some examples.